and welcome back everybody. So in this lecture I will talk about reaction kinetics. So how fast do reaction proceed to the left or to the right. First I start with this little video that I liked from Vijaya Rajadurai, taken from YouTube. I just thought it was nice because you have that little clock, that timer, and you can see the reactants going into products. So reactant A goes to B at some rate, and the rate then is the change in concentration over the time it took to get there, right? So it's pretty obvious what that should be, but again, that gives a good intuitive visual sense of, what that reaction rate R is, right? So it's really the change of concentration of A divided by the time, and also the change in concentration B, right? The appearance of B divided by the time. So if it's a simple A goes to B, then this is a very straightforward idea of the kinetic rate. Here, if we look at concentration over time, right? So concentration is in the y-axis, time is in the x-axis. There's different ways you can think of that reaction rate, right? So here, that would be a linear rate or a zero order. So the concentration is just a function of time. It doesn't depend on concentration. Now, here you can see that the concentration decreases as an exponential of time, right? And so that means that the rate changes with time, right? So it's faster at the beginning and then it's slower and slower and slower, right? You can see that slowing down. Now, if you log that y-axis, log C, right? Now you recover that constant rate of reaction in the log space, not in the linear space, okay? Now, if we look into a little more detail how we can define those reaction rates, again, remember that the rate is the change of a compound over time, right? And each compound will have a different reaction rate, constant. So here we can see that dA dt is, the concentration of A to the P, concentration of B to the Q. And again, P and Q are not the same as the stoichiometric coefficients, right? They're just different. So just remember that. They can just be, 101 or whatever, P plus Q. Now, there's a reaction rate for A, for B, and for C, right? They're different. They're just different things. Yeah, so RA and RB are the reaction rate for the disappearance of A and B, obviously. Remember that little movie we just saw. RC is the reaction rate for the appearance of C, the product. A, B, and C are the concentration, of course. Again, these are just rate constants that go in front, and P, Q, R are the reaction order with respect to a compound, right? To the indicated reactant or product, whatever that compound is. So again, remember that reaction order is with regard to one of the compounds. Now, if we look here, so one important thing here is that oftentimes when we describe reactions for environmental problems or groundwater transport problems, we assume what we call a first order rate, right? First order reactions. Now, in reality, there's very few reactions that are actually first order. Typically, we have reactions that are of this type, for example, where you have A to the P times B to the Q equals roughly A to the P because B is away from equilibrium. Meaning, again, if you have flux at the boundary, or if B is in large excess, let's say you have a compound A reacting to a compound B, right? And B is maintained at a high concentration by fluxes at the boundary. So let's say, in the aquifer, you just have that constant input of that carbon, a leak of organic compound, for example, in your aquifer that just maintained. Remember those 2D continuous source images that we've done in the previous topic, right? So you have situations where you maintain concentration artificially. So then basically the concentration never really changes. So it's essentially a constant. So it looks like the reaction proceeds at a rate A to the P and completely independent of B. I don't know what I clicked, sorry. Completely independent of B because B is essentially a constant, not affected by the reaction. If that's the case, if P is 1 here, right? If P is 1, then the reaction rate looks like this, right? It's just K times A. In other words, we can write this as, right, if K1 is little k here and we replace dA dt by dC dt, look at this. This is just a simple first order reaction rate, meaning dc dt is a function of c, like I described before, and there's a constant rate k, right? We can solve this easily, and we know that the solution of this equation, right, is an exponential, right? So if we do 1 over c dc equals minus k dt, right, we can integrate those two things. 1 over c becomes a log, k just becomes, so it's like log c equals minus kt essentially, and there's a c0, and then we can just take the exponential of those, right? So we get c equals e to the minus kt with a c0 here. Okay, so this is your first order reaction rate, first order reaction. And again, a lot of the let me get a little light here, it's getting dark in here. So many of the reactions that we model for, transport in water, we use this first order assumption, even though in reality, almost nothing is truly first order in nature. It's like typically, second or second order reactions, but we just assume this first order decay. Now, the only thing that is truly first order in nature is really radioactive decay, where you have that half-life, right? You can see here the number of nuclide versus time in multiples of t half, right? And t half is the half-life, meaning this is the time at which the concentration is divided by 2, just because there's that atomic click, right? It's just like decaying at its own pace, and that's just how it is. Now this is this is the only really reaction that is truly first order in nature. Now going back to the transport equation, I said before, what we do, right, is we take our advection dispersion equation and we tack on a new term. In this case, the first order reaction term here, again, remember dc dt equals minus kc, right? So minus kc, we just tack it on our advection dispersion reaction. If there is retardation, then there's a retardation factor right in front of here. And now we have an equation for the transport that includes retardation and first order decay. Now, if we plot this, you can see here the conservative tracer is blue, so let's say water, and then the reactive tracer is in green, and the net effect of a first order decay is, of course, the decay, right? We're losing mass, essentially, as time goes on. So we're losing more and more mass as time goes on. So you can see this illustrated here. Very little mass missing at the beginning, a little more, right? And then so on and so forth until it's completely all gone at some point. Okay, so that was a quick introduction to reaction kinetics, and especially to first order reactions, because that's a lot of what we use. In the next video, I will cover the monokinetics, so more like biodegradation, because again, when we do, let's say pump and treat, especially when there's treatment involving biodegradation. So if we are, basically counting on biological reactions to, remove pollution, then we're counting on biological growth, essentially. And so we'll see how that works. This is typically according to a monokinetic, as opposed to that first order simple kinetic that we've just seen. Thank you.